Hello everyone, welcome to the University of Lille in the north of France, and thank you very much for attending our Tech Corner. So we will present you a new method called the pit slope method to assess the HLB of all your surfactants, whatever they are, natural, synthetics or in complex mixture. So let's go.
Surfactants are of prime importance in cosmetic preparations. The choice of an appropriate surfactant is an important step to formulate emulsions and microemulsions. There are several methods in order to compare the hydrophilic-lipophilic balance.
How to measure the hydrophilic-hydrophobic behavior of surfactants?
In 1949, Griffin introduced the HLB, an empirical scale experimentally determined from stability of emulsions. In his first article, an exhaustive list of the HLB values is done from the lipophilic oleic acid with a value of 1 until the potassium oleate with a value of 20. Several years later, he proposed an empirical formula to calculate the HLB for the alkyl polyethoxylated alcohols. Then, Davis proposed a useful contribution method in order to estimate the HLB. However, there are big differences on the HLB values using both methods. Other parameters to describe surfactants are the packing parameter and the HLD. Packing parameter takes into account geometrical considerations to characterize surfactants. The HLD proposed by Zalager is a semi-empirical model to describe the formulation variables with a no-dimensional number. It takes into account not only the surfactant but also the oil salinity and temperature.
Why do we need another method?
For most cosmetic surfactant mixtures, these methods are difficult to use. Molecular structure not precisely known, or empirical experimental determination extremely time-consuming. That's why Cisco team developed the pit slope, a new simple method to characterize surfactants and determine their hydrophilicity through a temperature screening.
What is the phase inversion temperature?
Phase inversion temperature corresponds to the temperature at which the hydrophilic-lipophilic character of an ionic ethoxylated surfactant switches by the iteration of the polyoxyethylene unit during heating, leading to the emulsion phase inversion from oil in water to water in oil. The pit slope method is based in the gradual addition of a second surfactant into a reference system and then determine the change on the phase inversion temperature.
How do we proceed experimentally to determine the pit slope?
Step 1. Preparation of the reference system. The reference system is C10E4, N-octane, and an aqueous solution of sodium chloride. The C10E4 is a well-defined polyethoxylated surfactant. The weight of the oil and water are the same in order to privilege the behavior of the surfactant into the morphology of the emulsion and not the quantity of one of the two immiscible phases. At room temperature, this system presents a three-phase behavior, an equilibrium between the aqueous phase, a microemulsion with most of the surfactant, and the oily phase. This system was chosen because its phase inversion temperature is very close to room temperature. The experimental setup for the pit slope method is made up of a temperature-regulated bath, a small reactor with a magnetic steering system, a conductimeter, and a computer to record the conductivity values as a function of the temperature and time. The reference system is placed in the small stereoreactor connected to a thermostatic programmable bath at 18 degrees. Let's see the inversion. Here we have the conductivity temperature profile. At low temperature, the high conductivity increasing evidences an oil in water emulsion, because the external phase is the sodium chloride solution. Then there is a temperature range in which the conductivity drastically falls, indicating the inversion to a water in oil emulsion in which the external phase is the oil and the conductivity is close to zero. We can see that the phase inversion temperature of the reference system is near to 24 Celsius degree. At this temperature, the emulsion is unstable because the surfactant has the same affinity for oil and water. Step 2. Addition of the surfactant to characterize. The surfactant study is added in small aliquots to the reference system. In this case, we will study a commercial sophrolipid, a biosurfactant. For each aliquot of the sophrolipid, the phase inversion temperature is determined in the same way that for the reference system. Here we have the conductivity temperature profile, and we can see that the phase inversion temperature increases to approximately 29 Celsius degree after adding the sophrolipid. Now, let's see the aspect of the emulsion in the experiment. At the beginning, the aspect is white and quite homogeneous, but at a moment the homogeneity is loose and we can see different phases. In fact, since the surfactant has the same affinity for oil and water at the time of the phase inversion, it doesn't stabilize the emulsion. If the stirring is stopped, the phase separates. When the emulsion is reversed and the temperature is already above the PIT, the system will recover the homogeneity. Step 4. Determination of the pit slope. Here we can see how the temperature increases proportionally to the concentration of the sophrolipid. The slope of this straight line is called the pit slope, and it is a measure of the hydrophilicity of studied surfactants. In our example, when adding the sophrolipid, the energy needed to produce the inversion increases compared with the reference system. If the pit slope is positive, the surfactant is more hydrophilic than the C10E4, and if it is negative, the surfactant is more lipophilic. When the added surfactant is a mixture, as in the case of the sophrolipid, the concentration is expressed as a weight percentage. When the added surfactant is well-defined, we can express the concentration as the molar fraction. In this figure, we can see the phase inversion temperature as a function of the molar fraction for several well-defined polyethoxylated surfactants. The method is valid for non-ionic surfactant, polyethoxylated or not. What happens if we use an ionic surfactant? This figure shows some results for anionic and cationic surfactants, validating the proposed method also for ionic surfactants.
What to do with the value of pit slope? What are the potential applications?
When we get the pit slope value, we can compare it with the other surfactants and put it into a scale. Here we can see some technical grade biosurfactants like the studied sophrolipid and 2-mannosill erythritol compared with other commercial surfactants. Thanks to the pit slope method, we have characterized several commercial biosurfactants and saponins. The comparison can be done not only for commercial mixtures, but also for new well-defined pure compounds like isosorbate or glycerol surfactants. This diagram shows the place of several green surfactants compared with ionic and non-ionic molecules. A second application of the pit slope is to identify equivalent alternatives to replace surfactant in emulsions. For example, the bridge O2 is a petrosaur surfactant used in the formulation of water in oil emulsions. Mannosill erythritol MEL10 can replace it in the formulation because they have similar pit slopes. Additionally, the structure of the MEL10 allows get emulsions of isopropyl myristate in water as stable as those obtained with the bridge O2. A second example is in the coatings domain. Usually, ethoxylated surfactants are mixed with a very viscous resin, and then water is added progressively through a catastrophic inversion process to get an oil-in-water emulsion. In order to replace these molecules by greener surfactants, the typical molecules used in the process were tested and their pit slope evaluated. Then, greener molecules with similar pit slope values were used to get the oil-in-water emulsion.
Thank you for your attention. Do you have any questions?